Welcome back to Pharma-info with Shubhashish. Now today's topic is DAKIN reaction. Now DAKIN reaction involves conversion of an aromatic aldehyde. This is aromatic aldehyde with an additional hydroxyl or amino group, either at ortho or para position. So you're converting this hydroxylated aromatic aldehyde or amino linked aromatic aldehyde. When you are converting this into a diol species or amino-ol species, right, either at ortho or para position in presence of alkaline H2O2 and HCl, then you have to opt for DAKIN reaction. So it is the DAKIN reaction through which, if your intention is to convert the aldehyde which is linked to an aromatic moiety, and in addition to this we have a hydroxyl or amino group. If I want to convert both hydroxyl, then I need to charge this particular aromatic aldehyde with alkaline H2O2 in presence of HCl, right? What will happen as a result of this particular reaction? What will happen? I am supposed to get dihydroxy aromatic compound or amino hydroxy aromatic compound. Fine? Chalo. So now let's straightway move to the reaction mechanism, right? So let's talk about the mechanism, right? How this can be converted actually, right? So DAKIN reaction, as I am telling here, I have written here the alkaline H2O2, right? Now this alkaline H2O2 is basically the initiator, what we can say, right? Suppose in the step 1, I am charging this H2O2 with OH minus. Here I have written for the convenience of presentation, I have written only OH minus because this is found to be the reactive part of KOH or NaOH. Fine. So it's this H2O2 in presence of base. What will happen? This will produce what? Hydroperoxide ion, and it looks like this. It is the hydroperoxide ion that is getting generated once you are charging H2O2 with OH minus. That means the base. Fine. So it is the alkaline H2O2 that through which I can get what? The reactive species. That is nothing but hydroperoxide ion. Peroxide ion. In addition to this, okay, there is a generation of like this as well. Fine. But we are least concerned about these two other products, what we can say. Fine. Now let's, once we are done with this reactive species, what will happen? This reactive species need to be introduced into that reactor where this aromatic aldehyde is waiting. I am telling aromatic aldehyde, but the additional thing is it's not a solo aromatic aldehyde. Rather, to this aromatic aldehyde, either at ortho or para position, either hydroxyl or amino group is found to be there. Fine. Chalo. So for my convenience, here I have taken. So this is found to be the para hydroxybenzaldehyde. So this is para hydroxybenzaldehyde. Right? Fine. So we have with us what? The reactive species like hydroperoxide ion. Now let me do one thing. For the convenience of presentation, let me do one thing. Let me just keep this one in the proximal vicinity of this particular aldehyde. Fine. So we have an electron deficient center and we have an electron rich head. Fine. So what will happen? This will try to attack this area. Fine. This will try to attack this area, right? Fine. As a result of this attack, what will happen? A particular covalent bond is likely to form. Now once there is a formation of a covalent bond, what will happen to this pi bond? The pi bond will get broken and go on top of this oxygen. Fine. Chalo. So initially we got the first intermediate. So with that we are done with the formation of the first intermediate, right? So the first intermediate, how it looks actually. So the para-hydroxy will remain same, or that means it remains unaltered, right? Only thing is that, so here it's O minus, here we have O, then H, then we have a H. Fine. Chalo. So this is found to be the first intermediate that is getting formed, right? That has been formed here. Fine. Now what next? Now a triggering effect. We are expecting a triggering effect, right? Because now what is expected? So now we are experiencing a new thing, that is 1-2 shift. right? We are going to experience a new, phenomena or new scenario will come into place that is found to be want to shift, right? I want to shift this particular moiety, the entire moiety, I mean to say the phenolic moiety from here to here. Assume that this is found to position 1, this is 2, right? So that means I just relocate the phenol from here to here. As such, it won't change its location, right? It must get influenced by its neighbor, right? And this assistance is being provided by what? Provided by the cleavage of this peroxide linkage, right? Once it starts to break, what will happen? The entire pool will come here, right? The entire pool will come here. I mean to say the pair of electrons will come here, right? So what will happen to this oxygen? The oxygen will become monovalent, but that is not possible, right? So that means in order to make oxygen stable, what will happen? The entire pool, that means the phenol will try to shift along with the electron, which was earlier been shared between this and that, fine, to this center, fine, and thus this will come here. So that means it got the trigger from its neighbor, this bond got broken, fine. Once it has started breaking, what will happen? This will try to shift along with the electron, right, and try to find this place, because the deficiency has been created out of this breaking at this center, right? Once the deficiency, this is the center, I mean to say this is the center, right, which has become deficient, right? So now in order to replenish the deficiency, the phenol will come here, will try to relocate from here to here, right, fine. So once this phenol will try to come from here to here, what will happen? This electron has been taken up by this phenol. Now this has become what? Trivalent. So in order to fulfill the valency, what will happen? Again, this will try to come back to its native location. Earlier it was here, no? This carbonyl, right? So again this come here, right? So what will happen? What is that intermediate that is likely to be formed here? So now what happened? Again, this hydroxyl remain unaltered, right? The position of this hydroxyl remain unaltered. So what will happen? Now there is a formation of what? Like this. Another intermediate, right? Chalo. So this is as per the shifting. So this is called want to shift, right? Chalo. And why it happened? That we have just now seen, right? Now, what next? The next is acidic hydrolysis, fine. Acidic hydrolysis. Now it is the acidic hydrolysis, that means HCl at the same time water, aqueous HCl. Obviously, it's not an alcoholic HCl, it's an aqueous HCl, fine. That means it is the HCl that is basically induce the hydrolytic process, right? And it is that through hydrolysis, what will happen? This particular pair of electrons, right? That means now it is in covalent state, right? Covalent bond, right? This bond has to be broken and it should come here. And this occurs through hydrolysis, right? So it is the hydrolysis, acidic hydrolysis, that eventually give rise to the production of what? A phenoxide ion, hydroxylated phenoxide ion, fine. Now how it looks actually, let's see how it looks. Now, what next? Okay, so now here let us just write HCl, right? What happened? Through this acidic hydrolysis, what will happen? Another intermediate is likely to be formed, right? And here the intermediate is found to be like this, O minus, because as a result of this shifting, what happened? This turns to O minus, and this the fate of this hydroxyl is found to be always try to remain unaltered, right? Fine. What is the other thing that is getting formed? What is the fate of this portion? This portion will become something like this. Plus double bond O, and then we have a H, fine. So it is the hydrolytic degradation that eventually give rise to the production of this, right? But we are concerned about this, we are least concerned about this, fine. So what will happen to this? Now after that, what will happen? Once there is a formation of this phenoxide, we are left with one more step, right? What is that step all about? The step is simply charging it with water. It is the water that is basically releases what? The H plus, and which will be taken up by this phenoxide ion to form what? To form the dihydroxyaromatic compound, right? Dihydroxyaromatic compound. So this is the one, that means it can also be called as quinol actually. If I just try to name it, it can be called as quinol, right? The same mechanism has to be followed when the hydroxyl group is not here, rather here, fine? So at that time, if that is the case, if we start, if the starting material seems to be, the orthohydroxylated benzaldehyde, definitely you are not supposed to get the quinol, right? Instead of quinol, if I just opt for orthohydroxy benzaldehyde, then obviously the product will not be, quinol, rather it will be something like this, catechol, right? After all, it is the benzyl CHO that gets converted to hydroxyl, and the position of the hydroxyl remain unaltered all through the reaction. That we observe, right? All through the reaction, this hydroxyl remain unaltered, right? There is no change as such you observed with this hydroxyl, right? That means the para-hydroxyl, the additional hydroxyl will remain unaltered all through the reaction, right? So that is why if your starting material is found to be a para-hydroxybenzaldehyde, you're supposed to get what? Quinol. If your starting material is found to be ortho-hydroxybenzaldehyde, then your product will be catechol, right? One of the important, backbone of what? Norepinephrine or dopamine, what we can say. Fine. Chalo, the same thing. See, as I said earlier, that while starting up this session, right? The choice is yours. Whether you want to keep you want to start the reaction with a hydroxylated aldehyde or an amynated aldehyde. Fine. So if your choice is found to be an amino, this amino also will remain unaltered, right? So instead of getting quinol, if this location was substituted with amino, what will happen? You are supposed to get para-aminophenol. Same thing here also, orthoaminophenol, right? So that means whether it is a hydroxyl or amino, it remains unaltered all through the reaction. From the starting point to the end point, it remains unaltered. So it depends on your choice whether your starting material is having a hydroxyl or an amino group. Likewise, you are going to get either catechol or quinol or aminophenol or orthoaminophenol or para-aminophenol, right? So likewise, we can say, so this is how the entire process stands, right? Let me do one thing. Let me just project it in a proper way so that at least you can refer, right? While practicing, you can refer, right? So this is how the entire, mechanism went on, entire reaction went on, right? So initially what we did, we just started the reaction with H2O2. We just charged the H2O2 with OH minus, that means alkaline hydrogen peroxide. Then what happened? It basically generated what? Hydroperoxide ions, right? Once there is a formation of this hydroperoxide ion, then we just move on to the next step, that is we brought what? The para-hydroxybenzaldehyde, right? In presence of this hydroperoxide ion, what it basically did, it just the initial with this nucleophile, a nucleophilic attack was observed, right? Nucleophilic attack, right? It is the nucleophilic attack which subsequently give rise to what? Repositioning of what? The phenolic moiety from the carbon to the oxygen end, right? And likewise it just relocated itself from here to here, right? And it basically initiates when the peroxide linkage started breaking, right? Fine. And now we got this kind of stuff, right? And once we got this kind of stuff, then the acidic hydrolysis took place. It is the acidic hydrolysis that basically generated what? This phenoxide ion, hydroxylated phenoxide, what we can say, right? And after that, after catching one proton, right, what happened? This gets converted to a quinol, right? As I said earlier, that if your starting material is found to be an ortho-substituted one, then your final product will be catechol, and if it is found to be a para-substituted one, then your final product will be quinol, right? Same thing, instead of hydroxyl, you can start up the reaction with aminobenzaldehyde as well. If it is aminobenzaldehyde, obviously you are going to get para-aminophenol or aminophenol, right? It's up to you whether you have started with orthoamino or para-amino. Likewise, orthoaminophenol or para-aminophenol is found to be the product. Once you have taken, instead of this hydroxylated benzaldehyde, once you have taken amynated benzaldehyde, your product will be para-aminophenol or orthoaminophenol. So this is how the entire reaction mechanism stands actually. Entire reaction mechanism stand. Now let's move on to the few examples, right? Few examples. Okay, I'll give you one example, right? Or the applications, what we can say, right? Applications. We can say example or application, same thing, fine. Suppose ki, okay, you have taken, like your, as I said, okay, we know about para-aminophenol, the importance of para-aminophenol, right? We all know about paracetamol, right? So paracetamol is nothing but, assume that paracetamol is found to be the one, right, that we are after. So paracetamol is nothing but, it is something like this: all, then amine, then acetyl. Fine. So it's acetaminophen, acetyl aminophenol. Fine. So we all know that paracetamol is produced when with the proper union of acetic anhydride and para-aminophenol, right? Are we able to produce? Suppose you are running out of para-aminophenol in your lab, right? So in that case, but the thing is that in your lab, what you observe that a particular chemical is there which can be converted to a para-aminophenol. So what will be the chemical? Okay, suppose we all know that how to convert an aldehydic moiety into a hydroxyl. Fine. So if you are in the hunt of making para-aminophenol, right? Para-aminophenol. So para-aminophenol is found to be like this, hydroxyl and then amino. Same thing, fine, same thing. Chalo. So this is found to be the para-aminophenol, right? And this is not there in your lab. But in your lab, one product, one compound is there that is found to be like this. That is found to be like this. Para-aminobenzaldehyde, right? So in that case, definitely you are opting for what? If you are going to convert this para-aminobenzaldehyde into para-aminophenol, what is the additional thing that need to be taken? The additional thing need to be taken is, just now we discussed, what is that? That is nothing but H2O2, OH minus, that means the KOH or NOH, and HCl, fine. These three are the combinations that need to be introduced so that you can convert what? Para-aminobenzaldehyde into para-aminophenol. Same thing for orthoamino. If the amino is found to be located not here, rather here, then also you can get not para-aminophenol, rather orthoaminophenol, right? So thus you can produce what? One of the essential starting material for the production of what? The well-known drug paracetamol, right? So this is one example. Let me just put another example. Like here, suppose you have taken what? Your starting material is found to be like this, right? I'm just writing here. So we have a OCH3 here, and we have a hydroxyl, and here we have a CHO. Fine. So here actually we have not bridged the protocol. Fine. As per the protocol, you have to start the reaction with an aromatic aldehyde and make sure that aromatic aldehyde at its ortho or para position, hydroxyl or amino group is there. Fine. So likewise, both are there. Fine. Additional things that we have taken is OCH3. Definitely it will not hamper the reaction. Fine. If you are just introducing the reagents with which we can convert the CHO. Fine. So what will happen? Let us do one thing. Let me just introduce what? H2O2 NOH, at the same time HCl, right? I should write H2 as well, right? So what will happen? What is expected? Definitely, as both the functional groups are there and they are basically they basically stick to the fundamentals. So what will happen? The CHO is getting converted to OH, and this it remains unaltered, and we have a OCH3 over here, right? So thus we got what? Thus we got, can we say this is 3-methoxy-catechol because this is position 1, this one is 2, this one is 3, right? So can we call it as 3-methoxy-catechol? Yeah, we can call it as 3-methoxy-catechol. And what about the starting material? The starting material is orthovanillin. It is orthovanillin only, fine. Or in other words, in terms of benzaldehyde, we can say it's 2-hydroxy, 3-methoxy benzaldehyde. Fine. So we are done with one more chemical, right? One more chemical, right? This is found to be the product when our starting material is found to be vanillin or 2-hydroxy 3-methoxy benzaldehyde, right? And make sure that this combination should be there, right? The entire pool of reagent must be there. Otherwise, and we all know that the importance of each and every reagent, right? In transforming the aldehyde into a hydroxyl. Fine. Okay. So with that, we are done with the applications of this. Yeah, let me do one thing. Let me just project it in this way so that you can at least get to know. Fine. So applications of this DAKIN reaction. So hope you understood. Okay, the illustration, right? So with that, I'm concluding to this session. Now see you in my next video. And as I said, always please put your comments, right? And let me also know that which is the topic that you want me to discuss in my next video, right? So waiting for your response. Thank you.